Chapter 1.5, we're going to be going over more concepts about slope. So starting with parallel lines here. So two non-intersecting lines are parallel, and two lines are parallel if and only if they have the same slope. So parallel lines have the same slope. So let's do an example here, and it's going to be an example like we've seen previously. Let's write an equation of the line passing through the point -1, 3, and parallel to the line whose equation is y equals 2x plus 1, and we're going to write this in point slope and slope-intercept form. Okay, so starting with point slope form for the equation of the line, we have y minus y1 equals m times x minus x1. So we're given the x1, y1. We're given that it is -3, 1, and now we need the slope. So this time when we're looking for the slope, we're not explicitly told what it is. We're told that it's parallel to another line, and since these are parallel lines, they have the same slope. This equation that we're given is already in slope-intercept form, so we can just read off the slope here as 2. So that means our slope of our line is also 2. Okay, so let's plug in these values here. We get y minus 1 equals 2 times x minus -3. We can clean that up a little bit on the right. So instead of x minus -3, we just make that x plus 3. And now let's solve this for y to get it into slope-intercept form. So we have to distribute the 2 and then add 1 to both sides. Okay, so we end up getting y equals 2x plus 7 in slope-intercept form. So let's graph this. I'm going to graph y equals 2x plus 7 here. That would look something like this. And I'm also going to graph the line that it's parallel to, y equals 2x plus 1, for comparison. So that's y equals 2x plus 1. So when we graph them, it becomes a little bit more clear that these lines are parallel. Okay, so let's do another example here. So let's write an equation of the line passing through 5, 0, and parallel to x minus y plus 2 equals 0. Okay, so starting with point slope form again. We have y minus y1 equals m times x minus x1. We know that x1, y1 is 5, 0, and we need to find m. So this time when we're using our equation to find the slope, because once again, we know that we're parallel to this other line, we first need to rewrite this other line in slope-intercept form. So if we are solving this equation here on the right for y, all we have to do is add y to both sides. We would get x plus 2 equals y, or just y equals x plus 2. So the slope of this line is going to be 1, because there's a 1 there that's not written. So that means our slope is also going to be 1, since parallel lines have the same slope. So let's go ahead and plug those values into the point slope form. So we get y minus 0 equals 1 times x minus 5. And let's go ahead and solve this for y. It's essentially already solved for. And we get y equals x minus 5, and that is our slope-intercept form. Okay, so I'm going to graph this, and I'll graph the line that it's parallel to. So graphing y equals x minus 5, we end up getting this line right here. And now let's graph the line it's parallel to just to make sure. That's y equals x plus 2. And we can see that we most likely did it correctly. These lines look like they are parallel to one another. Okay, so those were parallel lines. Now for perpendicular lines. So two lines that intersect at a right angle or a 90-degree angle are perpendicular lines. The slopes of perpendicular lines are negative reciprocals of each other. So this means that the product of their slopes is -1. So to find a negative reciprocal, we have to first negate the number and then take the reciprocal, or vice versa. So if the number was negative and we negate it, it becomes positive. If it was positive first, we negate it, it becomes negative. Okay, so let's see an example here. So let's write an equation of the line passing through -3, -5, and perpendicular to the line x plus 2y minus 8 equals 0. And starting, just like we've been starting, with point-slope form. We have our point-slope form, we have our x1, y1, -3, -5, and as usual, we need the slope. So this time we are told it's perpendicular to this line. So this line is not in slope-intercept form, so let's solve this for y first and get it into slope-intercept form. Okay, so what we have to do here is we have to subtract x and add 8 to both sides. So we'd get 2y equals -x plus 8. Divide both sides by 2. We get y equals -1/2 x plus 4. So I divided the -x by 2 and just rewrote it as -1/2 out front, and divided 8 by 2 and got 4. Okay, so the slope here is -1/2. So the slope of our line is going to be the negative reciprocal of -1/2. So instead of negative, our slope is going to be positive, and the reciprocal of +1/2 is 2. So our slope is 2. Okay, so let's go ahead and plug everything in here. We get y minus -5 equals 2 times x minus -3, and let's clean that up a little bit. So that gives us y plus 5 equals 2 times x plus 3. This is our point-slope form, and let's solve this for y. We have to distribute the 2 and then subtract 5 on both sides. So we end up getting y equals 2x plus 1. So let's go ahead and graph y equals 2x plus 1. So here's our line graphed. Now let's graph this line right here that we were perpendicular to, just to verify that that is correct. Y equals -1/2 x plus 4. And we get this line right here. So taking a look at this, it does look like these are intersecting at right angles. Looks like it's 90 degrees at that point where they're intersecting. Okay, so let's do one more with perpendicular here. So let's write an equation of the line passing through -2, 6, and perpendicular to y equals 2/3 x minus 1. So starting with point-slope, we have y minus y1 equals m times x minus x1. We have our point, x1, y1, -2, 6. And we are told that it's perpendicular to y equals 2/3 x minus 1. So our slope is going to be the negative reciprocal of this one's slope. So this one's already in slope-intercept form for us. So we just have to find the negative reciprocal of 2/3, which is going to be -3/2. So -3/2 is our slope. So let's go ahead and plug everything in here. So we get y minus 6 equals -3/2 times x minus -2. Let's clean up that right-hand side a little bit. And when we clean that up, we get y minus 6 equals -3/2 x times x plus 2. And that is our point-slope form. And now solving this for y is a little bit more difficult because of the fraction, but not too much. We have to distribute the -3/2 and then add 6 to both sides. And we get y equals -3/2 x plus 3. Okay, so let's graph these. Let's graph the one that we just found, y equals -3/2 x plus 3. And that would look something like this. And now let's graph the line that it was perpendicular to. It was perpendicular to 2/3, y equals 2/3 x minus 1. So let's graph that as well. And we get that line right there. And we double check. It looks like they do cross at a 90-degree angle. Okay, so for the next thing, we're now going to be thinking of slope as a rate of change. So when we're calculating slope and we're thinking of it as a rate of change, what we're going to have to do for a final answer is we have to make sure we keep track of the units in the numerator and the units in the denominator. So let's see an example here with this graph. So this following graph, it shows the number of women and men living alone from 2000 to 2013. And for our question here, we want to find the slope of the line segment for women, and we want to describe what the slope represents. So we're only doing it for the women one, so we're looking at this line right here. So let's find the slope for that line. To find the slope, we need 2 points, which they're given to us right here and right here. So these 2 points are going to be our x1, y1 and our x2, y2. So I'm going to say x1, y1 is the point 2000, 15.5, and x2, y2 is the point 2013, 18.6. So we're going to use these points here to calculate the slope. And we know that the slope formula is m equals y2 minus y1 over x2 minus x1. So using those points from right up here, let's plug those in. So we plug those in, we get 18.6 minus 15.5 divided by 2013 minus 2000. So evaluating this, we get about approximately 0.24. Okay, so now we need to think of what this means. So what this means is going to be, since slope is y, the change in y divided by the change in x, it's going to be the units of y divided by the units of x. So the units of y is going to be the y-axis, and the units of x is going to be the x-axis. So this represents the number in millions living alone per year. Okay, so we can write that as 0.24 million, which is 240,000. 240,000 women living alone per year over this interval. So the units of y for every or per unit of x. So women living alone for every year. Okay, so far that last example that we just did, for example, those were examples of linear functions. It was a straight line. So let's say that the graph is not a straight line. Then the average rate of change between any 2 points is going to be the slope of the line between those points. The line connecting those points is what we call a secant line. Okay, so the average rate of change between the points, x1, y1, and x2, y2, is going to be just the slope. So for a linear function, it was pretty simple because linear functions have constant slopes. No matter what interval you look at, the slope is always going to be the same. So something like what we have right here on the graph on the left, this blue curve is clearly not linear, so the slope is going to be changing as we go. But if we want to figure out what the average rate of change is from this point, x1, y1, to this point, x2, y2, all we have to do is calculate the slope between those points. So we know the slope formula is m equals y2 minus y1 over x2 minus x1. We're not going to be explicitly always given the y2 and y1. We have to know that these represent the function values. So we have to remember that y equals f of x. So what that means is for our slope formula here, y1 is going to be the function evaluated at x1, and y2 is going to be the function evaluated at x2. So we're going to have to find their corresponding y values by plugging the x values into the function that we're given. Okay, so before we get an actual function here, let's take a look at just a graph. And let's say we want to find the average rate of change between the points labeled on the graph. Okay, so we can see that we have a man and his height in inches is recorded every year. And we want to come up with the average rate of change between when he was 13 to when he was 18. And we can see that secant line connecting those years. Okay, so I'm going to let x1, y1 be 13, 57, the first point, and I'm going to let x2, y2 be 18, 76, the second point on the graph, and the slope between them is going to be our slope formula. So let's go ahead and plug in these values. So we get m is 76 minus 57 divided by 18 minus 13, and we end up getting 3.8 for this slope. So let's think about what this means. It's going to be 3.8 units of y per units of x. So it's going to be 3.8 inches per every year. Okay, so we would say the average rate of change is 3.8 inches per year over this interval. That means on average, he grew 3.8 inches for every year from when he was 13 to when he was 18. So even though this clearly is not a linear growth that he's having, it's not a straight line, we were still able to find the average rate of change over an interval using the slope formula. Okay, so let's do an example here where we're not given the graph. Let's find the average rate of change of f of x equals x squared from x equals 0 to x equals 2. So we're going to need the slope formula. We have m equals y2 minus y1 over x2 minus x1. So this time we're not explicitly given y1 and y2. We have x1 and x2. So we're going to have to use the fact that y1 equals f of x1 and y2 equals f of x2. Okay, so using these facts, it becomes f of x2 minus f of x1 divided by x2 minus x1. So we have to evaluate f of x2 and f of x1. So for f of x1, that's going to be plugging x1, which is 0, into our function. So it's going to be f of 0, which is 0 squared, which is just 0. Now for f of x2, that's going to be f of 2. So evaluating f of 2, that's going to be 2 squared, which is 4. So now we can plug those in, and we get 4 minus 0 divided by 2 minus 0, which ends up giving us 4 over 2, which gives us 2. Okay, so average rate of change is 2 over this interval. That means on average, the y values changed 2 units for every 1 unit that the x value changed. So let's take a look at the graph of this. Our function was f of x equals x squared. So let's graph this. So here's f of x equals x squared. It's a parabola. And we were looking for the average rate of change from 0 to 2. So from 0, that's the point 0, 0, that's right here, to 2, that would be this point up here. So the average rate of change from that point is going to be the slope of the line connecting them. So if we connect those 2 points as a straight line, that is the secant line, and the slope of that line is 2. So we found it algebraically, doing it by hand up here. We got an answer of 2, the average rate of change, and we can see by looking at it, this does look to be like a slope of 2. Okay, so bringing us here to one more thing. It is the difference quotient. So let's consider the slope between 2 points on a curve, just like we've been doing, essentially the secant line between 2 points. So here's our curve, and let's say we have a point here, and that's going to be some arbitrary x value, and let's say we have another point here, and instead of that value given some arbitrary letter name, we're going to say that it's a certain distance away from x. We're going to say that this is h units away from x. So if it's h units away from x, we can actually call this point x plus h. Okay, so let's see the secant line between them. Okay, so there's our secant line connecting those 2 points. And if we want the slope of the secant line, we know what it is. It's just the slope formula. So y2 minus y1 over x2 minus x1. So we're going to be using these 2 points, x and x plus h, as our x2, x1, which seems probably a little bit confusing. So we need to figure out their y values. So let's figure out their y values. Well, if our function is f of x, that means the y value for just x here is going to be just the function evaluated at that point x. So not very helpful. For the other point, x plus h, that's going to be this y value over here, which is going to be f of x plus h. So all we're doing is plugging in those x values into the function, which are just these generic letters right now, and those give us out the y values. Okay, so let's go ahead and plug those into y2 and y1. So y2 is going to be f of x plus h, and y1 is going to be f of x. So I'll make a little note here. x1 is going to be our x, and x plus h is going to be our x2. Okay, so for the slope formula, it is now going to become m equals, let's just replace it here with the function version of it, f of x2 minus f of x1 over x2 minus x1. So remember, this is just the same thing but different notation like we did on the other page. And now let's plug in using our x and x plus h. So f of x2 is going to be f of x plus h minus f of x1. F of x1 is just f of x. So that just boils down to what we said x1 and x2 were. And this is going to be divided by x2 minus x1. Once again, we're just using this idea. That's x plus h minus x, x2 minus x1. And if you notice here in the denominator, the x's actually cancel. So with the x's canceling in the denominator, we're left with the slope of this secant line between x and x plus h is f of x plus h minus f of x. So once again, that's just the difference in the y-coordinates divided by h. And we have to remember here that h represents the distance between the points. Okay, so hopefully makes sense a little bit here. Probably doesn't seem why it's useful. So let's see why this is useful. So what we just found, which was right over here, the f of x plus h minus f of x divided by h, what we just found is called the difference quotient. So the difference quotient is a very important ratio that is essentially helps us with the foundation of calculus with limits. And like we mentioned, it's going to be the average rate of change of the function from a point x to a certain distance h away from x, which is x plus h. And in calculus, what we're going to be doing is we're going to be taking what we call the limit as that distance approaches 0. So what this does, it gives us the instantaneous rate of change at a single point. So taking a look at this graph up here, let's imagine that distance, h, let's imagine it getting smaller and smaller. What that means is this point is going to get closer and closer to our point x because that distance is getting smaller and smaller. So that secant line second point is going to be approaching that point itself. So let's take a look at a GIF or a GIF here. So here's our function, and the fixed point x is on the left. It is the black one. The red one is x plus h. The distance between them is getting smaller and smaller. Once it gets directly on top of it, that line gives us the instantaneous rate of change. It's called a tangent line, and the slope of the tangent line would give us the instantaneous rate of change at that single point x. So essentially it's like the instantaneous slope at a single point rather than the slope between 2 points. Okay, so let's do one question here by hand. So let's say we have f of x is 2x squared minus x plus 3, and let's find and simplify the difference quotient. Okay, so what we have is our difference quotient for our function f of x. So what we're going to do is we are going to plug in f of x into right there. We're going to substitute it. The difficult part is first we have to find f of x plus h, and then our goal is going to be to cancel h in the denominator. Okay, so let's keep that in mind for the end. So first, let's just find f of x plus h, since that's the more difficult part. So f of x plus h, all we're going to do is plug in an x plus h everywhere we see an x. So that's going to be 2 times x plus h squared minus x plus h plus 3. And we have to simplify this a little bit. So simplifying this, we would have to FOIL out x plus h squared. That would give us x squared plus 2xh plus h squared minus x plus h plus 3. And let's distribute now. Distribute the 2x squared plus 4xh plus 2h squared minus x minus h plus 3. We would try to combine like terms, but there's no like terms, so that is our f of x plus h. Okay, so pretty messy. So let's plug that in or substitute it into this part of the equation right here. So it's going to end up being 2x squared plus 4xh plus 2h squared minus x minus h plus 3. So that whole thing is f of x plus h minus f of x. F of x is just our function. We have to make sure we have parentheses around it because we're going to have to distribute that negative in front of it. And this is all divided by h. Okay, so once we get this, what's going to happen? Since we have a polynomial, this will always happen for polynomials, we can completely cancel off f of x using what we have on the left. So let's distribute that negative. I'm going to drop the parentheses. And let's distribute that negative on the right. So that's minus 2x squared plus x minus 3, all divided by h. And now let's see what cancels out. We have 2x squared minus 2x squared cancels, negative x plus x, and 3 minus 3. Okay, so let's see what we have left over now. So we have 4xh plus 2h squared minus h all over h. And let's factor out an h in the numerator. If we factor out an h in the numerator, we have h times 4x plus 2h minus 1. So that's just factoring out essentially greatest common factor. And now the h cancels. So once again, that was actually our main goal, is to cancel that h in that denominator. And we're left with 4x plus 2h minus 1. And this is our difference quotient for our function f of x, which was 2x squared minus x plus 3. And it's completely simplified. Once again, if we were in a calculus course, what we would be doing is something called the limit definition of the derivative. We would be taking the limit as h goes to 0, which means now we would plug in 0 into h. This would give us something called the derivative of the function, which would tell us the instantaneous slope at any point x on the function. So we won't worry too much about that right now, but for now this is the difference quotient simplified for a function. So something to think about here, this is clearly not, f of x was clearly not a linear function. If we had a linear function, so in the form mx plus b, if we worked out this difference quotient for it, our answer would just end up having a constant as our answer. So there'd be no more x's in it, it would just be a constant. And that's because the slope of a linear function is constant no matter what x gets plugged in. It's not dependent on x. Okay, so that is it for chapter 1.5.